and welcome back. And this will be the last of the series of videos introducing you to the basics of advanced hard uncertainties. After this, we'll go on to actually trying to carry out some measurements and calculations without this video support. So you'll be doing some at-home experiments without me running alongside you. So in this video, we are going to take two measurements and combine them in a calculation. These measurements will have different units, so we'll need to use the final uncertainties formula that's in your formula sheet that allows you to combine the uncertainties with completely different units, completely different measurements to get an overall uncertainty for a final quantity. I'm going to use the absolute classic of distance, speed, time today. So we are simply going to calculate the speed of any object doing any distance. It could be a ball rolling along the floor, it could be you running a certain distance, it could be you throwing the object to, well actually that's pretty tough to time. Rolling an object along the floor is probably going to be your easiest thing, but any distance with any set of times. We'll repeat our timings 5 times again, and then we'll set about on our calculations. So let's set up our data table together, and then you can pause this video and go away and take your measurements. So we're going to have an independent variable of the distance here. Now we're only going to do one distance, but it's the thing that we're going to choose. You know, why not do a meter or something? You could do a little bit longer and reduce the reaction time issue. So once again, my measurement uncertainty will be half my smallest division of my measuring device to measure out that distance. And then we'll have time in seconds. And I think I'm going to be using my just my normal stock clock on my phone. So we established that was to 2 decimal places plus or minus 0.01 seconds. 1, 2, 3, 4, 5 mean I'm going to run out of space. Again, I'm not sure why I've left delta C out of my list here, but I would recommend delta U, delta C, delta T, and I'm going to pop in a delta D column as well, because we're going to have our distance, but our distance is going to have 2 associated uncertainties. Even though we're not repeating the distance, it is going to have the distance measurement, it is going to have its reading uncertainty, and it's also going to have its calibration uncertainty. Okay, so there will be a couple of things to take care of there. Sorry, I'm cheating there, not using my ruler. Okay, so pause the video. Oh, I've made those lines too long. That is frustrating. Pause the video, away you go, and just measure any distance and roll something along it 5 times and measure the time, and I'll see you back here for processing that data. See you in a moment. Okay, so I redrew my table. I had to. It was annoying me too much. You can see that my numbers went over the lines. It was awful. So I'll quickly redraw my table. So here I am with my repeats. I was just rolling the same green ball that I was dropping earlier to do our ut plus half at squared experiment. I just rolled it along the floor for a rough distance of 2 meters. I'm sure it's not quite, but you know, it's just an example. So let's have a little check about your attention to detail and your precision. So if I am saying that the reading uncertainty of my device is to 0.5 millimeter, I need to make sure that I am recording my data to that same level of precision. Okay, so thousands of millimeters, hundreds of millimeters, tens of millimeters, individual millimeters. I actually need another 0 on there for 0.5 millimeters. There we go. So I know it seems pretty odd, But if I am genuinely recording a reading uncertainty of 0.5 millimeter, then I'm saying that that is how precise I can be using this measuring device. So what I'm saying here is the distance was exactly 2 meters. It wasn't beyond by any dashes. So there were no, the distance was right on the line from 0 to exactly 2 meters. And this reading uncertainty says that I can be that precise. The calibration uncertainty for the ruler was the same as my larger ruler, but actually if I'm going to make this a little bit more like the classroom, then I'm actually going to say that it's like a meter stick. So if I just show you this, and like I say, I've attached this to the descriptions. So a wooden meter stick has a calibration uncertainty of 0.5 millimeters. Okay, so I'm just going to pop that underneath. I'm going to say that delta C here was 0.5 millimeters. That's 0.5 times 10 to the minus 3 meters. Okay, so my uncertainty in my distance is the square root of my reading uncertainty plus my calibration uncertainty, no repeats. That's the square root of 0.5 squared plus 0.5 squared.
So I've obviously forgotten that I zoomed in earlier. Don't worry, I do zoom back out quite soon.
0.7 times 10 to the minus 3 meters. Okay, and I can just pop that straight up here. So that is, just to make it match, 0.007. Nope, that's wrong, isn't it? That's going to give me 1, 2, 3, another 0. Yeah, that's right. 1, 2, 3, 4, 1, 2, 3, 4. So let's go ahead and get our mean values and, sorry, there we go. Get our mean values, our random uncertainties, and our total uncertainty in time. So if you want to pause this video here, you work on your values, I'll work on mine, and we can compare in just a second.
So you can see me getting confused here because I've realised I've forgotten to calculate my delta C, and that is because I would normally have it as part of my table. Have it as part of your table, folks.
So remember guys, I'm going to go for that kind of standard calibration uncertainty here just to get you practicing using it. The percentage can change, it can be 0.3%, 0.2%. So I'm just taking a number since I don't actually know the calibration uncertainty from the stopwatch for my own phone. If you don't know calibration uncertainties, you can leave them out, okay? So I wouldn't suggest you make one up when you're actually doing your experiments and your investigation at all. But you do quite often come across them like this, so I just want to give you a chance to practice them. Or just see how that kind of uncertainty is used. If you don't know the calibration uncertainty, or if you Google the calibration uncertainty for whatever you're using, you may well find it. And certainly anything that's actually specifically designed as a measuring device, such as a voltmeter, an ammeter, any of these things, micrometers, traveling microscopes, they will all be published with a very well-known calibration uncertainty. But if you can't find one, you just simply put a note next to your data table saying calibration uncertainty unknown and leave it out.
Well, now I'm really going off the rails because I've just left that calibration uncertainty without a unit. May as well pause me here and get ahead, folks. I'll see you with your delta D and delta T.
All right, folks, so I hope you've had a chance to calculate your mean, your random uncertainty, and had a chance to bring together your total uncertainty for your time. Yours might just include a reading uncertainty and a random uncertainty if you didn't know the calibration uncertainty for the device you're using, which is very, very common. You will not be penalised for it if you genuinely can't find it. You do have to make a bit of a check. When you're actually doing your assignment, have a good Google for the calibration uncertainty for any of the measuring devices you are using if your school doesn't already have a record of them. And if you can't find it, then the likelihood is the marker can't find one, and therefore it's perfectly reasonable for you to say that you just simply don't know it. Okay, so we have our distance and an associated uncertainty. We have our time and an associated uncertainty. Now you can imagine, guys, say this was a proper experiment and we would have multiple versions of this going down. So I would have ever increasing distances, times for them all, and each of those would have this going on. You would still only need to show the calculations for those total uncertainties one time. You only need to show the method for attaining all your uncertainties one time, and then after that you just show the final results. And that is why using spreadsheets is so useful. If I was doing this data on a spreadsheet, I could simply fill in this first column. I would get the spreadsheet to calculate this for me by putting a calculation into the spreadsheet, calculate this for me, this and this, and then just click on the little blue square and drag down, and it would populate the rest of the time of the table for me. So it really is worth your time and effort learning how to put calculations into spreadsheets and get them to work hard for you, and learn those skills now than punch away on your calculator and getting all these uncertainties.
The tutorial to make a table like this in a spreadsheet is in this playlist.
Just ignore those uncertainties while you're doing that. So let's find V. So V equals distance over time, and that is 2.0000 over 3.09 equals, for me, I get 0.6, and I'm limited to 3 sig figs because that is the least amount of sig figs my raw data has from my times. So 0.647 meters per second. Okay, I do have 5 significant figures from my distance, but only 3 significant figures from my time. Calculations are controlled by the lowest number of sig figs going into that calculation. Okay, so there we are, there's my speed. So let's try and find delta V. Oh, little v for speed. Okay. So here I'm combining uncertainties that have different units, and that involves an entirely different formula. Again, it's on your formula sheet, and on your formula sheet it looks like this. So just like we did in higher, to be able to get rid of the units, we turn things into fractions. So this is just like percentages, guys, except we're just leaving off the times by 100 stage, that's all. If it makes you more comfortable, you can actually just put percentages in here and know that you'll get a percentage out. That's absolutely fine. I'm teaching the official formula here, but it is actually okay just to put percentages in here. You get your percentage uncertainty out, and then you calculate your absolute at the end. So again, we're going to make it specific to our calculation here. So this is going to be delta V over V is equal to the uncertainty in my distance over my distance squared plus the uncertainty in my time over time squared. So that's equal to 0.0007 over 2, which is tiny, plus 0.04 over 3.09. So you can see here, guys, that proportionally, my distance uncertainty is tiny. It's going to be negligible here. So delta V over V comes out as this. I'm going to put the whole thing in anyway, just because this is demonstrating. So actually I need a bracket there, and you can, the lovely thing with modern calculators, you can do this entire thing in a oneer and it can look exactly like your page, allowing the really good pattern recognition software in your brain to spot if there's any mistakes and disparities before, plus you press enter like that one. All under the square root. There we go. Okay. So it is, I'm actually going to take that off and I'm just going to say delta V equals. So now that I've got my my square root, this section, I'm going to multiply that by my speed, which is 0.647, say equals, and that comes out as 8 times 10 to the minus 3, 0.008 meters per second. Okay, so that's an absolute uncertainty, folks. It requires a unit. So just to be clarify what I did there, I put this whole thing into my calculator, and then for this final line, I multiplied that answer by V to get rid of this fraction over here. Okay, so now all it leaves me to do is write my final statement. So V equals 0.647 plus or minus 0.008 meters per second. 3 decimal places, 3 decimal places. All matches up. Answer's not more precise than my raw data. And there we go. So that there, folks, was your introduction to this combining formula, which allows you to combine for any units, any data that is of different units. Now, the most common time you're going to be doing that is when you're multiplying things together and dividing. So before we go on to try and use these skills all together in a new kind of measurement, let's just do a summary of the new formulae and stuff that we've come across so far.
If you haven't calculated the final uncertainty in your V, pause the video now and go and do that first.
So, we've got calibration uncertainties, call this the summary. And they are stated by the manufacturer. Okay, and they are added to all raw data. Okay. You've got combining uncertainties with the same unit. And this can also be adding and subtracting. Separate measurements with same unit. So an example of that would be the V minus U for A equals V minus U over T. V and U would be totally separate measurements, but they have the same unit, so they could use the same unit formula to get the uncertainty for that section on the top of the fraction there. So that is the delta W equals the square root of delta X squared plus delta Y squared plus delta Z squared. If we're wanting to combining uncertainties with different units, that are multiplied or, sorry, that word is or, not of, or divided then it's the fractional uncertainties we use. Okay, and that really is a total summary. Oh, we've forgotten the powers. Uncertainty of a raised power. So if we've got x to the n, then delta x to the n is equal to n times the percentage uncertainty in x.
You could now try the uncertainty tutorial that's attached in the description of this video.
Okay. So to bring this all together and try out something that's a little bit different and a little bit more challenging, our kind of final activity in this particular series is going to be measuring the density of a baked bean can. At least I'm going to be using a baked bean can. You can literally use any can whatsoever. A cylindrical can, it doesn't matter what's inside it. It doesn't matter if it's a small squat can or anything. But the calculations that we do will all be the same. And this is going to allow, this process is going to allow us to bring all of the skills that we've learned together. We're going to have different measurements, we're going to have powers, constants, all sorts of fun things going on. So I'll see you in our next video where we bring our uncertainties all together and measure the density of a baked bean can. Thanks, folks.